Hello everyone, and welcome back for the second and final talk in my series on SL2C Floer Homology. In this talk, we will define a knot invariant using SL2C Floer Homology, and we'll also discuss some computations of the three-manifold invariant for surgeries on knots. So recall that last time we defined sheaf-theoretic SL2C Floer homology for closed orientable three-manifolds, denoted this invariant HP of Y. Today we're going to define a very similar invariant for knots. So for K inside of Y, a knot in some three-manifold, we'll define what we call the tau-weighted sheaf-theoretic SL2C Floer homology of K, denoted HP sub tau. Here, tau is going to be some complex parameter that we'll say a little bit more about later. And what we'd like to do is establish some properties of this knot invariant, and also we'd like to compute the three-manifold invariant for surgeries in some knots. So first, I would like to go over the construction of the knot invariant. I'll do this a little bit quickly because it's completely analogous to the construction of the three-manifold invariant with some minor modifications. And just as before, the input that we'll need is a Heegard splitting, this time of the knot complement. So first, I'd just like to say what I mean by that. So given a knot inside of a closed orientable three-manifold, pick two base points on your knot, K, and that allows you to define a sutured manifold for the knot exterior, where the suture is, in this case, will be a pair of meridional curves on the torus boundary of E sub k, the exterior of the knot. Those two meridional curves divide the torus boundary into two pieces, two cylinders, which are usually called the positive and negative portions of the boundary. So then a Heegard splitting for the knot complement is a decomposition of the exterior into two handle bodies glued along a surface with boundary. In this case, the boundary of the surface is going to be the pair of meridional curves. And the handle bodies will have boundary given by that surface together with some portion of the boundary of the knot exterior, either the positive or the negative portion. So in this case, maybe U0 has the positive portion and U1 has the negative portion. Just as before, the relevant moduli spaces for us will be character schemes, though in this case we will have to consider the relative character schemes, which are defined as follows. They're something that you can associate to a group with fixed conjugacy classes and some complex parameter tau. Then we have the tau-weighted relative representation scheme of the group, relative to these conjugacy classes and the parameter tau. It's the set of all homomorphisms to SL2 for which the trace of the homomorphism on that conjugacy class is equal to tau. And once again, we can form the GIT quotient with respect to the SL2C action by conjugation to form the relative character scheme, tau-weighted relative character scheme. And we will also, as before, mainly be concerned with the locus of characters of irreducible representations, chi, tau, ear of gamma. So we can define our knot invariant HP tau of k via the same recipe that we used last time. It turns out that for tau not equal to plus or minus 2, well, for tau equal to those values, that's the trace of the identity, or plus or minus the identity, in SL2C, and that's not good. What we want is, away from those values, the relative character scheme of the surface sigma. Remember, sigma is a surface with two boundary circles, so we're considering representations that send those circles to elements with a trace tau. That turns out to be a holomorphic symplectic manifold, and once again, the relative character schemes of our handle bodies are Lagrangians inside of it, exhibiting the character scheme of our knot exterior then as a Lagrangian intersection. So on this Lagrangian intersection, we can form the natural perverse sheaf as given by Boussi's construction. And it turns out then that this is an invariant of the knot. And we'll call its hypercohomology the tau-weighted sheaf-theoretic SL2C Floer homology of the knot. Just as our invariant before was inspired by instanton Floer homology, this is supposed to be some type of singular instanton knot Floer homology using the gauge group SL2 instead of SU2. Now, I should say a little bit about this theorem. This theorem was first proven, well, the first part was proven by Coté and Monolescu in their construction of this invariant. They prove it for tau between a real parameter between -2 and +2. And Coté and I extended this to all values of tau not equal to ±2. Well, as I mentioned, for tau equal to ±2, you wouldn't even consider this construction because at those values we don't even have a holomorphic symplectic manifold. But at all the reasonable values of tau, it turns out to be an invariant. So I should say a little bit about why this extension was required, why it was initially proven only for a much smaller set of values. Essentially, the issue is just showing that this perverse sheaf is independent of the Hagar splitting. So it turns out that if you had two different Hagar splittings, let's just say one is a stabilization of the other, then you can definitely try to define an isomorphism between the two perverse sheaves that you get. Well, at least you can define this isomorphism provided you can match up the spin structures appropriately. And that might be a little bit difficult to see how that works. So we get a little bit lucky if the Lagrangians are simply connected, because then they'll have a unique spin structure, and there's no question of matching them up. And for tau, a real parameter between -2 and 2, Coté and Monolescu were able to use a diffeomorphism between this character scheme, relative character scheme, and the moduli space of parabolic Higgs bundles. And in those, for the range of values, those spaces had been computed, and it turns out they're simply connected. So what Coté and I did was we applied the theorem of Verdier to show that for all the finitely many of the taus, all of these character schemes are all going to be homeomorphic. You can imagine it's sort of an algebro-geometric generalization of something like the regular value theorem, which would say that away from some critical values, all of the fibers of this trace map, a meridional trace map to the complex plane, should all basically be the same. And then you can extend to the remaining finitely many values of tau, you can extend the proof of invariance by using what's called variation of weight data on Higgs bundles. Okay, so I didn't want to write that all up here, just to give you some sense of how the proof goes and what's relevant for this theorem. In the next segment of the talk, I'd like to discuss some properties of the not invariant HP tau established by Coté and myself. The first natural question one might ask is how the invariant depends upon the complex parameter tau. It turns out there may always be some special values of tau for which you get some different answer, but that generically one might hope HP tau to be independent of the parameter. We don't prove this, but what we prove is the analogous statement for the Euler characteristic of HP tau, which we call the SL2C Casson-Lin invariant of the knot, in analog to the situation in gauge theory, in which the Casson invariant is related to the Euler characteristic of instanton Floer homology associated to the knot. And we show then that this quantity is, the Euler characteristic is generically independent of the parameter tau. Let me give some sketch of the proof to show why we use the Euler characteristic and not HP. Essentially, it's because the Euler characteristic has an alternate interpretation as just the Euler characteristic of the scheme on which the sheaf lives, that is the relative character scheme of the knot complement. Its Euler characteristic weighted by something called the Behrend function. So one imagines that this scheme has some stratification. The Behrend function is some constructible function with respect to the stratification, and we take the Euler characteristic with respect to that function. The upshot is that the bare-end function is actually an invariant of the scheme. So unlike the perverse sheaf, which in principle could depend upon the way we've written our scheme as a Lagrangian intersection, the bare-end function only cares about the scheme structure. And this is good because this means that in order to prove our theorem, we really only have to show that at the various different values of tau, we're getting the same scheme each time. We don't have to show anything about the perverse sheaf on those schemes. So that is in fact what we prove. It's just a simple theorem about bare-end functions in algebraic geometry. What we show is that if you have some map from a complex scheme to A1, and we consider the fibers over various points, and consider the Euler characteristic of those fibers as weighted by the bare-end function, then those quantities are all generically the same. In other words, there's some open set, some dense open set inside of A1 for which these Euler characteristics are the same. You could think of this maybe as a generalization of something like the regular value theorem in differential topology. And so our theorem about the generic independence of the SL2C Casson-Linn invariant, the generic independence of the parameter tau, then follows by taking, in this theorem, taking x to be the character scheme of the knot exterior, not relative, and f the meridional trace map, so that the various fibers of the map f form the various relative character schemes weighted by different numbers. Another property one might consider is how the invariant behaves under taking connected sums of knots. For instance, one might hope that HP of a connected sum is just the direct sum of HP of the sum ends. But this will not be true. What is true, what we show, is an additivity at the level of Euler characteristics. So first we need to define what we call the sheaf-theoretic SL2C Casson-Linn invariant. We define it to be the generic value of the tau-weighted Casson-Linn invariance. So remember, at each value of tau we defined the Euler characteristic of HP tau as the tau-weighted SL2 Casson-Linn invariant, and then we proved that actually all these quantities are generically independent of that number tau. So let's call that generic value some number that we associate to our knot, the Casson-Linn invariant. And now let's take knots inside of homology 3 spheres and form their connected sum. In this situation, we prove that the Euler characteristics, that is, these Casson-Linn invariants, are in fact additive over the connected sum. And the proof is as follows. So the character scheme of the knot exterior basically has three kind of separate pieces. Well, actually, there might be many disjoint different components, but we can separate them out into three sort of classes. Two of the pieces are just actually copies of the character schemes of each of the sum-end knots. And then there's a third piece. There's a third piece which are representations that don't correspond necessarily to representations of one knot or the other knot, but it turns out that this piece has a free action of C star. Essentially, what you imagine is the circle, or the meridians along which the two knots are glued together to form their connected sum. By twisting around this meridian, essentially conjugating with elements in the stabilizer of that meridian. So the meridian gets sent to some value, not plus or minus 1. So its stabilizer is a copy of C star inside of SL2C, and conjugating with that action, essentially twisting on that meridian, provides some free action of C star on these types of representations. And then having such an action makes its Euler characteristic equal to 0. So you can see here clearly then that, of course, this does not really generalize to the case of the perverse sheaves, because in the case of the perverse sheaves themselves, it it would be more than just the sum of each of the two, because there's this third piece to your scheme. And in fact, that third piece is in general higher dimensional than each of the two pieces coming from the sum ends. In the next segment of the talk, I would like to discuss some independent work of mine computing the three-manifold invariant for surgeries on knots. So this won't actually be related to the knot invariant we were discussing earlier. This will be using the three-manifold invariant we defined last time. So we'll be considering knots inside of the three-sphere, and we'll let S3 sub P over Q be the P over Q Dane surgery on that knot. And we're interested in computing the three-manifold invariant for those manifolds, perhaps relating those groups to each other. The simplest class of knots for us will be small knots. Small knots are those which have no incompressible surfaces in their exteriors. In that case, it turns out that the character scheme of the knot is one-dimensional. This follows from Collar-Shallon theory. They did some of the earliest work in applying character varieties to low-dimensional topology. The main theorem they have is a way to associate incompressible surfaces in closed three manifolds to ideal points on curves, ideal points of curves in the SL2C character schemes of those three manifolds. And that result quickly implies the statement I've given here. And in particular, this means that for kind of most values of P over Q, that the character scheme of the Dane surgery is zero-dimensional. Well, that's just because the character scheme of the P over Q Dane surgery is like the same as the character scheme of the knot. You just add one extra equation corresponding to setting P times the meridian, or the pth power of the meridian times the qth power of the longitude, setting that quantity equal to 1. That adds an extra equation on your character scheme, and so it'll be then going from one-dimensional to zero-dimensional, at least most of the time. So in that case, the quantity here, the invariant HP, is nothing more than just a count of the irreducible representations, because we just have a zero-dimensional scheme. And the invariant will then just be a copy of Z in degree 0, one copy for each of these points. Well, it turns out that this count of irreducible representations was already defined by Cynthia Curtis. It's called the SL2C Casson invariant. Hopefully that's not too confusing with the sheaf theoretic SL2C Casson invariant that I just defined. Essentially, that's some sort of refinement of this. So the theorem that one quickly gets is that in the case of a small knot, at least for most values of P over Q, calculating HP, it reduces to calculating this Casson-Lin invariant. For those finitely many values, you can go ahead and compute the answer by hand, just by computing the character scheme by hand in those cases. For example, I computed the character schemes for the trefoil and the figure 8 knot by hand, and thereby obtained a full formula for HP of the surgeries for all the values of P over Q, including the exceptional cases. Now, for non-small knots, it becomes a lot more difficult, because the character scheme in that case will be positive dimensional and potentially quite singular. And then identifying the relevant perverse sheaf becomes difficult. It turns out that if the character scheme is smooth, then the perverse sheaf has to be just a local system with stalk Z placed in degree minus D. So for smooth character schemes, we pretty much know exactly what it is. If they were smooth and simply connected, then we would actually know exactly it to be the constant sheaf Z placed in degree minus D. But once singularities appear, then I don't at least have any great way of identifying what the relevant perverse sheaf is. So these calculations of the three-manifold invariant for knot surgeries, other than just being interesting examples in their own right, perhaps, the initial motivation was for establishing some type of surgery formula for HP sharp. Remember, HP sharp was the framed version, which takes into account the reducible representations. It uses the representation schemes. I didn't actually carefully define it, but it's defined in some fairly analogous way to the unframed invariant. So in the framed situation, you might wonder if there's a surgery formula. Other Floer theories, like Floer Homology or Instanton Floer Homology, have surgery exact triangles, at least for the framed version. So if you know about Floer, think that HP corresponds to like HF red, and HP sharp would be more like all of HF. And of course, HF red doesn't have an exact triangle. So you could ask the same question about HP sharp. Is there an exact triangle like this from the P+1 surgery to the pre-surgery to, and then here we have the infinity surgery, just S3. Well, if you're familiar with some of those other exact triangles, you might think I've got this one backwards, but actually since we're using kind of a cohomology theory rather than homology, everything goes the other way. But what I have shown is that it cannot be such a surgery exact triangle, at least for the trefoil. This theorem follows just from a calculation of the relevant representation schemes. Well, at least a partial calculation is good enough to establish this theorem. Most of the representation schemes, at least for the trefoil, actually do turn out to be smooth by some miracle, just because the trefoil is quite simple. But there are a few exceptions. Essentially, I think it's when p is divisible by 12, so 0, 12, 24 surgery, etc. Those have singular representation schemes, and in those situations, I cannot identify the perverse sheaf, and so I can't compute the invariant in those cases. But at least the data from all the other cases is enough to conclude that this exact triangle could not possibly exist. To conclude, I'd like to offer some further directions for future research about these invariants. So the first, I think, maybe most important thing that personally I would like to see done are some computations of the invariant in some non-trivial situations, meaning when the schemes are actually singular. In those cases, we would need a little bit more technology to try to understand these perverse sheaves, and I think that's something someone with some good algebraic geometry background could maybe attempt to do. Another question would be how to relate HP or HP sharp of a knot surgery to the knot invariant HP tau. That seems like a natural question. It's one that I have not really thought about much. Another is this conjecture that I have about a certain invariant a certain set of invariants one can extract from computing HP of the knot surgeries. So if you consider just, let's say, the rank of HP in degree n of the P over Q surgery, and it could be HP or HP sharp. So consider this quantity and normalize it by 1 over Q, and take the limit as Q goes to infinity. So I claim these are well-defined knot invariants. This conjecture is actually templated on something called the SL2C Casson invariant for knots as defined by Bowden and Curtis. So they make an analogous definition where here HPN, that quantity, is replaced by their SL2 Casson invariant of a 3-manifold. So in that way they extract an invariant for knots somehow by finding this asymptotic quantity for the Dane surgeries. So I've computed HP for the trefoil and the figure 8, and that I verified this conjecture in the case of HP for the trefoil, or HP sharp for the trefoil, and HP for the figure 8. But it would be interesting to see if it does hold in general, and if so, then this is some new knot invariant, and how does it relate to HP tau, the other knot invariant. Thank you for listening, and please direct all questions towards the conference forums. I will try to get to your questions as soon as possible.